before I get started, I want just to cover my background a little bit. I started this company called Scalar Research. We're basically an AI and data science consulting firm. But before that, I spent several years at Stanford and a couple of years at the Stanford AI Lab doing research on computer vision, particularly in healthcare applications. So today I want to talk primarily about four things. First, I'm going to cover what is face processing, what are the main tasks, and the kind of things people are trying to solve in this field. Second, I'm going to cover some of the topics in computer imagery that are going to help us understand the challenges and the solutions we have for face processing. And third, I'm going to talk a little bit about the techniques for machine learning and computer vision that people leverage for face processing. And then finally, using everything we learned in the first three sections, I'm going to finalize with a couple of techniques and a couple of practical examples. So we're going to learn how to build some prototypes or proof of concepts that leverage all those techniques and do some things with like face processing. So let's get started. First, we're going to look at a couple examples of what people are trying to solve in face processing. The first and most basic task we have is face detection. This is basically the idea behind localizing faces in pictures. You can have this by itself being useful. For example, if you have a camera, if you detect the faces, it can help the camera focus on the right areas of interest. This is useful both for the software because it shows a lot of areas of interest for the software to focus on, and also for the user. So we can have this in terms of like monitoring tools, in terms of like input for downstream facial recognition tasks, and so on. So the idea here is that faces are usually areas of interest, and by localizing the faces, you can do more complex things, be it by the person or the computer itself. So this is a fundamental task. And then once you detect the face, the second part is recognizing who the face is. So facial recognition then corresponds to, for example, what we have in Facebook photos, where once you have a picture, they detect a face, they're also trying to say who this person is. You can do this from a sample of people you already know. For example, on Facebook photos, they know all your friend groups, your own face, so they look at those faces to try to determine who you are. This can also be without knowing who the actual person is. So for example, in Apple Photos, they try to cluster similar faces together, so they don't even know who the potential people are. They just look for similar faces in this database of photos you have. And then finally, you can also use this for biometrics and security and other applications like that. Another important task is face classification. Here, you're trying to infer some properties of the face. It's not about the specific person, but about some metadata about this person. So for example, you could try to classify the gender of the person. You could try to classify emotions. You could try to estimate ages and a number of other properties. For example, is the person wearing glasses or not? Did the person close their eyes in the picture? There are a number of common tasks that people are trying to solve like this. And then another very important one that's becoming more and more common is face manipulation. Here you're trying to modify or add some features to the faces. This is very common, for example, as Snapchat filters. So as you detect a face, you detect the facial features, you can modify the shape, you can add new objects to the face, and do several things like that. So applications range from more serious ones, let's say like Photoshop and other things like that, to the more fun and casual applications like this. And this is just a small sample of what people are working in the field. There are several other tasks, for example, gaze estimation, where you try to detect where the person is looking at, face orientation estimation, where you're trying to see the angle of the face in the picture, 3D reconstruction, where you start with a photo of the person and try to construct a 3D model, and so on. So this is just a general idea of what people are working on in this field. And then next I want to talk a little bit about computer imagery and how it all affects computer vision and face processing. So the general idea we have is that an image is a grid of pixels. So if you have a picture like this, you have very tiny pixels, and each pixel, in general, corresponds to a color that's based off 3 channels. So you can represent colors in multiple different ways, but the most common one is the RGB model that has 3 values, basically 3 channels, which corresponds to fundamental colors, that is red, green, and blue. And if you combine those colors, then you come up with the different colors that your computer can represent. So this is the idea here. You can combine those fundamental colors to come up with all the different colors you have. And depending on the color model you have, you can represent different types of colors. And in general, RGB can correspond to most normal colors people use for computers. So basically, combining these two ideas, an image is a grid of pixels, and each pixel is corresponding of multiple channels. We have now basically a 3D data structure here. So we have X and Y for the pixel location, now the channel, which is also known as the depth in an image. So if you have an image, you're going to have this width and height, and if you're using RGB, basically 3 layers of this. This is in machine learning and other fields known as a tensor, which for the intuition is basically a matrix in higher dimension. And the intuition for programmers more easily is just a nested arrays with fixed length. So in this case, you're going to have 3 level deep of arrays for the width, the height, and the channels here. And basically, if we try to visualize this, this is the whole idea. We have those matrices that are overlapped on each other. And again, so the tensor now, if you generalize from just the X and Y, now you also have height and width, and now the channels as well. And why is this important? The importance here is that if you look at a picture, you have a lot of parameters. So for example, if you take an iPhone X that has a 12 megapixel camera, and then you take a picture of that, that corresponds to an image that's going to have about 4,000 pixels wide and 3,000 pixels height, and then again 3 channels for each of those pixels, so you're going to have about 36 million parameters for this. So if you're trying to do some machine learning on top of an image or something like this, if you have each data point having 36 million values, you're not going to be able to build anything meaningful with the model unless you're able to do something smarter than just treating them as random values. So if you look at a picture like this, you're going to have 36 million values for a picture of a dog. And in order to come up with something useful here, you're going to be able to extract meaningful features from this huge amount of data that you have. So this is where machine learning and computer vision come in. If you just use standard machine learning for images, it's not really going to work. That's why you need to bring in some techniques from computer vision that can learn some meaningful ideas or insights from imagery data. Traditionally, people have approached this in 2 ways. We have the more traditional computer vision methods, where you start with some algorithm that tries to extract meaningful features from your images, and then using those features, you train a machine learning model to make your predictions. And then more recently, deep learning became more popular, and the advantage of deep learning is that it can learn how to extract the features automatically. So basically, you start with a neural network, and then this neural network is going to learn how to extract some of the features, and then be able to make the predictions. So I'm going to cover a couple of examples for both to just give some motivation here. So for the traditional computer vision side, a very common technique is called HOG, which stands for histogram of oriented gradients. And the idea behind it is that you can summarize a picture by splitting the picture into small grids, and then for each of those cells, you're going to compute the gradients, which means the directions of changes in colors and things like that. And then for each of those cells, you compute that, and then you just combine for each of the cells that you have in the picture. So the idea here, if you have a picture of a face, for example, you're going to split this picture into several cells. And for each of those cells, you're going to summarize the information that's contained there. With HOG, you're computing the gradients or the changes in colors. This could be a lot of different ways to do this. And then you're just going to concatenate this for all the cells you have in the picture. And then what we get after we do this with the HOG, for example, is that for each of those cells, you're going to get the directions that are more common in the picture. So they basically summarize what are some of the common facial changes or the facial features that can happen in each of those cells. And then if you combine that across enough data points, so a lot of faces, you come up with the picture on the right, which is a summary of what faces generally look like. So if you combine then what this generic version to the specific data point you're comparing, you can...
one small question. When you say you have a lot of sets of pictures of faces, it means different humans Because it's possible that one person could manipulate his face as he wants. So maybe do you use a data set of one person with different emotions on faces? How it's working? Do you incorporate this thing?
So the more variability you have in your data set, the better it's going to work, the more it's going to generalize. So if you have, for example, a data set that's a single person, a model that learns on that data set is going to be very good to recognize that specific person, but it's not going to generalize that well to other people. And again, in terms of you're talking about the expressions and let's say emotions and so on, if you have, let's say, enough variability in terms of like positions of the faces, facial expressions, and other features like that, then again, you're going to be able to generalize. So you basically have a trade-off here. If you want to be very good at solving a single task, then you're ideally going to have a data set that has only that particular thing. Let's say, be it a specific person, a specific angle, let's say a frontal picture or like a side picture, a specific facial expression, something like this. Or you could go for, let's say, a more generalized approach where you try to solve this for a higher population or something like this. And in doing so, your average performance is going to be a bit lower, but you can do that across multiple different sorts of images.
Okay, thank you very much.
Perfect. So this is what people used to do several years ago, but now people are starting to do more with deep learning. So the idea behind deep learning and neural networks, in a very summarized way, is that you have several layers in this network, and each layer is going to combine the information that it takes and basically output new information. And by having multiple layers, the model can basically learn more abstract or compositional knowledge about your input. So in this case, if you look at the picture, your data is the green points, and then it basically combines that to create this intermediate representation that in blue, recombines that to create another intermediate representation, and then finally comes up with the output that you want for your model. In the case of computer vision, most commonly people are using convolutional neural networks. The idea is, again, pretty similar to those grids, but instead of splitting this in actual grids, you're going to look at every possible sub-image of your image. So basically, you're going to take a small square and slide that around your whole picture, and for each of those small squares or small cells, you're going to try to extract something meaningful. So you might be looking at, for example, 5 by 5 pixels or 10 by 10 pixels, and then from those, you're going to create some intermediate representation of that, and then you're going to start combining those. So in practice, this looks like this. In the first layer, you're often going to learn very primitive features about your image, so they're going to be on the top left, for example, just strokes or directions, things like that. So this is looking at the very granular level of the image. And you're going then to start combining those features. So then from those strokes, you can go for small shapes, and then shapes you progressively can combine them until you start, for example, identifying some facial features or faces and things like that. So the idea behind a convolutional neural network is that you can start looking at the very small scale to identify what is in all those small parts of the image and start combining that information, hierarchical or compositional approach to come up with the final representation you have. So in general, neural networks tend to perform better, but they have some trade-offs as well. First, you need massive data sets for them to learn anything meaningful. And second, training can be slow and sometimes very tricky in terms of getting the right parameters, the right configurations, and so on. But oftentimes, the main advantage we have nowadays is that there are a lot of pre-trained models out there, especially, for example, for face processing. So you can download someone else's model, and a lot of researchers or companies have published those. And then starting with those models, you can fine-tune the existing models to your specific task. So you have a model that has learned to do general things about either computer vision in general or face processing, and whatever you're trying to do after with that for your specific task, you can start with this model and only change, let's say, the last mile of the problem. So this simplifies the problem a lot for you. And then finally, now I want to cover some of the actual face processing techniques. This was all like a background review of the things we want to do. So let's actually dive into a couple examples here. The first one is, again, we're going to start usually with face detection. We can do this with the convolutional neural networks. We can do this with HOG and several other techniques. And if you want to do this with open source code, it's actually very simple. There are libraries out there that allow you to, with pretty high accuracy, detect faces and other things like that with just a couple lines of code. So for example, in Python, there are libraries such as face recognitions that in 2 lines of code, you can load an image and then detect all the faces in that image. And it's going to return the coordinates for the faces in that image. And then using this, you can then start looking at the more interesting tasks you want to tackle. One of the interesting concepts here is called the embeddings. Basically, you're going to, the idea behind embeddings is that you're going to map whatever samples, be it faces or other things you're working with, into this coordinate system, which basically means a vector. And the idea behind it is that similar objects are going to be close to each other in this vector space, and then the similar samples or the similar objects are going to be far from each other. And you can do this for graphs, words, sentences, and also for faces. So the idea here, for example, if you have the faces from the same person, you could, in this embedding space, they should be close to each other in the vectors, and different people should be far from each other. And similar here can actually be defined as however you like. You can do this for the same person. You can do this for a similar characteristic. So it could be, for example, emotions, gender, and so on. So you could have like an embedding where it's embedding for the emotion in the picture. So people with like similar emotions and so on are going to be close by in this embedding space. And again, with libraries, you can extract those generalized embeddings. So for example, the same library I mentioned, you can take a general embedding of a couple lines of code. And the interesting part here is now that we have those vector representations for faces, is that you can actually do a lot of useful things just from this. So for example, we could start to replicate Facebook photos using only those lines of codes. First, we can start by collecting face embeddings that we know about different people. So for example, if we already upload your profile picture or friends have tagged you in pictures in the past, you can collect the face embeddings for those pictures. And then whenever someone uploads a new picture, you can compare the embedding from these new photos to the known embeddings that you have. And if anything is close, then you know it's likely the same person. So that's how, for example, Facebook makes recommendations for whoever is pictured in there. And using only those 4 lines of code, which is a pretty simple method, we can actually get something that works pretty well. So here's the distance in terms of like the embeddings that we have. So if you take the vectors and compare the distance between the vectors, we can see that the same person, even though they have different lightings or different angles, the same person has the smallest distance compared to the other person. So it's a pretty reliable way that that generalizes pretty well to the conditions of the pictures, to different facial expressions, to different lighting conditions, and so on. So basically, you're trying to get this general representation that represents the person irrespective of whatever exact conditions they had in this picture. Then a next step we can start to do here is look at the facial landmarks themselves. So the idea here is that you want to locate the key points in the face. So for example, those are going to be points representing the facial features like eyes, the nose, the mouth, the chin, and so on. So depending on the model, we're going to have some key values, for example, let's say 5 points corresponding to the main features, or a lot of points corresponding to very detailed representations of the face. So for example, here we have a model that creates, I think, 68 points. So those are going to represent several points in the chin, several points in the nose, the mouth, the eyes, the eyebrows, and so on. And again, this is something that's very simple to do with open source libraries. The same library, you can extract the landmarks, and that's going to give you all those different points for the different features that you have. You're basically going to load the image, detect where the faces are, and then pass this through to the library, and it gives all the points for each of those features. And again, using something like this, we can create something that starts to get interesting, such as Snapchat filters that I mentioned before. The idea here is that once you've detected a face, you can use a method like this to extract the facial landmarks in the picture, and then you can place new objects on top of those landmarks. You can distort the image. You can draw lines or things on top of it. So here's a quick example of what we can do. Again, this is something that we're going to be able to do with very few lines of code, but it's going to be pretty interesting already. The idea here, what we're doing is that we're loading an image in the first line, and then once we've detected the landmarks, we can start drawing some polygons in Python here. So we're going to draw basically red polygons for the lips and dark polygons for the eyes. And with this, we can create a automated makeup procedure. So if we start with a picture on the left of the girl, we then detect the landmarks. The landmarks are going to show us where the specific facial features are. And then just by drawing some polygons, we can create some new version of this picture that, even though it's not the best filter you've ever seen, but it was just a couple lines of code, we were able to add like lipstick and other makeup products to this image. So this is pretty simple, but you can get creative with this and start placing objects. So for example, the Snapchat has like common, let's say, dog filters, where you're just basically detecting the different landmarks and then placing existing objects into those landmarks. And then in some cases, it can start to get creative if you combine this with other tasks. So for example, I briefly mentioned that you can also have the 3D pose estimation, where you're estimating where the person is looking at, and so on. And by combining that information with the landmarks, then you can create pretty accurate and pretty realistic filters or modifications on the faces. And then finally, I just wanted to touch on how to actually do face processing in practice. There are dozens of libraries out there that people are commonly using. Some of those are focusing on the simplicity. So for example, for this talk, I talked about this library called face recognition, which is really focused on simplicity. You can 2 or 3 lines of code solve for the most common face processing tasks. And then you can also go for the more flexible libraries that have a lot more power. So for example, FaceNet is one of the very common but powerful methods for extracting face embeddings that you can then use for classification and so on. Or there are models that are implemented directly on TensorFlow or similar technologies, for example, inside face and so on, that then are achieving the state-of-the-art performance. So here you have a trade-off between performance and flexibility, and also the simplicity and the speed of the model. So depending on the task or what kind of requirements you have for your task, this is something that you have to choose. And also, I think it's important to know that if you're working with this at scale, you don't necessarily have to deploy your own models. There are a lot of vendors out there that have almost state-of-the-art, or actually the state-of-the-art performance in most of those tasks. And you can do this in a pretty cheap way. So for example, with AWS or Azure and similar platforms, you can usually process 1,000 faces for $1 or less. And then you're going to, basically with those APIs, you're able to get very detailed information, for example, ranging from the features from the faces to classification, from like gender, age, and so on, to more on the recognition side. They can detect celebrities, they can detect if you upload multiple pictures, who are the same people there, and so on. So in other cases, it might be a lot faster and a lot cheaper to actually use an API like this than deploying your own models. So this is what I wanted to cover today. I'm happy to answer any questions, and also please feel free to email me if you have any questions later on. I'm happy to chat about this.
You mentioned at the beginning that you can use this sensor with 3 layers of color, right? Red, green, blue. Do face recognition usually use them exactly like in 3 colors, like RGB? Or is there any benefits in using some other color spaces? For example, like in image compression or video compression, they use other color domains like luminance, chroma.
Yeah, so the most commonly, especially for deep learning, people are using RGB. I think one of the advantages of RGB is that the deep learning model is then able to infer a lot of the other images like that. So in theory, a neural network should be able to start with your original RGB representation and go for the other representations. So you don't necessarily have to do that. And also one of the advantages is how generalizable it is. So especially since you're working with models that can be trained once and then applied to different fields, so people tend to default to the more standard approaches like RGB. So I haven't seen, for example, anyone work with like semi-YK or other models like that for in this field.
Thank you.
Hello, thank you for presentation. I wanted to ask you, did you have chance to work or maybe hear about matching person face with the character or behavioral patterns? So you can recognize by face, is he dangerous to the people, or is he psychopathic or something like that. So by feeding a face to a system to recognize his expected behavior, or like in general. I understand that all people are different, but in some cases, face can represent this activity.
I haven't seen anything like that in practice myself, but in theory, if you have those relationships in real life, then a model like this should be able to learn those things. So I guess it's more of a question is, are those relationships between the face and those character conditions actually there in real life? And if so, then a model should be able to pick up on those nuances in the face and make those links as well.
Thank you.
So it's like China.
What about watermark recognition?
Sorry, can you repeat that?
Watermark recognition. You know this symbol sign here. When you, I don't know, open a picture on some photographer share inside, and they put watermark to protect it. Yes.
Mm-hmm.
So do these algorithms work with this kind of problem, and maybe you know what can people do in 2019?
Just to confirm I understand what you're asking, are you talking about removing the watermark from a picture, or?
First of all, recognition where it is, and then you remove it.
Okay, so in the case where you have a picture and there's a watermark, but you can still see the face, that should still be fine, especially with the more recent models, because people are also adding samples like that to your training set. So if you start training a model with images that also have watermarks, then the model should, in theory, be able to learn to generalize to that as well. And I guess this then to the second part, in terms of like removing the watermark. I've seen some work with techniques called GANs, which for generative adversarial networks, that take the input like a watermark picture and then tries to output the same image but without the watermark. So there's some work there.
Okay, and the last question. So when we have this RGB picture, we have a lot of details. I cannot see, or this JPEG format, what they do to save space. So does this artificial intelligence will it help to save space? So we recognize the features which we want to save in higher resolution, and all other parts of the image should be blurred.
Yeah, so I guess the way it starts, as you input to the neural network, it can go for the very high resolution image or something like this, where you're going for each pixel and then the 3 values for each pixel. And then as it progresses through the network, you can start to compress down this representation of the face. So for example, especially I mentioned like the face embeddings or just general embeddings for pictures, those often have much lower dimensions there. So I mentioned, for example, an iPhone X picture has 36 million parameters as an input, but a lot of those face embeddings, they have, for example, 128. So you're going from millions to hundreds or thousands of parameters there. And it's basically taking all that raw information and trying to distill the essential information. The same way you see when you look at a person, you're not thinking about each individual pixel, you're looking at the general characteristics in an abstract way, but so you're looking at some important features there. This is exactly what the neural network is trying to do.
Okay, suppose I upload my picture somewhere network. So you having my picture, you able to create 3D model of my face, yes?
Yes.
Okay, having 3D model, you could create it on 3D printer some model. Based on that, I have looked a lot of videos where iPhones was unlocked by a mannequin, something not without light. Understand what I'm talking about?
Mhm.
So with these technologies, everyone could create a 3D model of another face and upload it and not any iPhone, suppose. Is there some face IDs that have great depend from this one or less depend? Sorry, I was property what.
Yeah, in theory, you should be able to do that. I think in terms of the 3D reconstruction, I think we're not there yet to have very precise or very accurate representations. I think the sensors are in a better stage right now, but I can see, let's say in a couple of years, we're at the stage where you can create like very accurate 3D models just from a couple pictures. Maybe not from like a single picture, but once you combine several pictures from you, especially at like different angles, different lightings, and so on, you should be able to create like a pretty accurate 3D model. In the same way you see in movies with like CGI and so on, you start to get some pretty accurate 3D representations from people. And then using those, I'm also not sure where the stage where current 3D printers are, if they can create something that's as realistic as that, but I think this is also going to start to become a challenge. It could be a challenge in the future.
Okay, thank you very much.
Sorry, I missed in the beginning what the company is doing exactly, but I know that you are investigating these connections between faces. Can you please give a brief information what exactly your company is doing? Not you as a person in the research lab in university, but this one. Thank you.
Oh, so the company Scalar Research?
Yeah, because
So it's a consulting company, so working on like different fields. It's broadly in AI, especially deep learning, so things ranging from NLP to computer vision, and working in particular with the more traditional kind of company. So for example, one of my recent engagements was with a chemicals company that had dozens of millions of PDF documents of chemical data stored in a server, and they basically came to us asking, can we do something with this data and so on. So it started like OCRing those documents to extract the text, try to extract some structure from those documents, and then finally come up with some insights. Also starting to do some work on the pure computer vision side as well. So for example, monitoring logistics inside manufacturing plants, so tracking trucks or license plates, people, like that. So it ranges a lot depending on the client. It's a consulting company, but broadly doing a lot of computer vision and NLP.
thank you.
I have a question about bringing similar images together. As I see, you're talking about some kind of clusterization, where you want to group the same person or the same emotion. What data are you using for this task? Is it the initial image, the output of the neural network, the weight of the neural network, or something else, some features? What is used for this bringing together?
Yeah, so you mean for the embeddings?
Right.
So your data set is probably going to have something like either you start with the clusters of like the pictures, so you can have, for example, pictures of like similar people. You know already when you're training the model, you have a data set has, let's say, 10 pictures from hundreds of people or thousands of people. Or you can start with a data set that's labeled in terms of, for example, let's say the emotions, like the facial features. You basically need some sort of data set, and that has like whatever feature you want to start clustering in. And then basically this model is going to take the input as the picture, create this whole representation, and as it's training, it's trying to output this vector, let's say 128 values, and the network itself is training to, you basically give two pictures to the network, and if they're the same person or the same characteristic, it's going to try to approximate the output from those two, and if they're not the same, it's going to try to distance those 2 points.
So it's done on the labeling stage, right? So what you meant about bringing together is actually about labeling the data before training?
Yeah.
And not actually extracting the data. Because I got the wrong impression that you're using some training information to cluster images based on some features. That you can theoretically train a complicated model for face recognition and then use some form of twisted clusterization in order to group up some clusters of emotions.
Yeah, so you start with the data set, for example, with the emotions, and then this model, you're going to feed pictures into it, and if you feed similar, the model is going to learn basically end to end, so it starts with the image itself and outputs this vector, and if you feed, during training, you're going to give pairs of pictures usually, and if you give like a pair of pictures that have the same emotion, it's going to try to output similar vectors for the two images. And if they have different features, then it's going to try to output vectors that are far from each other.
Thanks.
Any other questions? Okay. I think this will be the last one, because our time is getting down.
Thank you for the presentation. I want to ask, can you explain emotion by part of face?
Sorry, can you repeat that?
Part of face. On top of maybe this emotion. Can you recognize emotion by part of face?
Exactly. So behind the scenes, what the neural network is doing, it's looking at the different expressions you have, and from that trying to identify the emotions. Usually it's not creating an explicit representation of that, so it's not going to have the specific, the explicit representations for, let's say, the positions of your different facial features, but it's basically doing that behind the scenes in a more abstract way. You could, if you wanted, have this intermediate step, so if you wanted to go from the picture to, let's say, the facial landmarks, and the landmarks then are going to have the actual shape of the picture, and then from the landmarks predict emotion, you should also be able to do that. But in general, I think starting with the raw image that end-to-end to the emotions, that tends to work better, because then you're also going to learn the network should be able to learn some features that are not obvious to us humans, or things that we're not explicitly laying down as important for this prediction, but that it might also be able to pick up in the same way that we pick up some features as humans that we don't really explicitly realize as we're doing it.
So thank you, Gabriel, one more time.